look at your titration quiz, you can ignore this 0.81. This was just to show you guys how you should box up your answers. Alrighty. So we are going to take some new notes. Now, before we get to that, you don't have to write anything down on this slide. I want to go over a couple of reminders. Okay, a couple of reminders. So the pencil can be down right now, just reminding you of a couple of things. Moles equals mass over formula weight. Been there, done that. Just a reminder, this is only for pure stuff. So if I have a solid chunk of something, 9 out of 10 times. Every now and then we'll have a pure liquid. That's pretty unusual. Okay. But if you have a pure, solid, something like that, especially if you start seeing grams thrown around, you know this is probably where you're going. Okay? Now, we also looked into this equation, the molarity equation, where it's moles divided by volume. And this is for solutions only. This applies to solutions only. Now, some people are like, well, Mr. Professor, why don't we just use the formula weight thing? Like, what's the deal? Again, the reason why we can't use formula weight is because the solution is more than 2 chemicals. It's something dissolved in water. Water's got a formula weight of 18. Whatever's dissolved in it probably doesn't have a formula weight of 18. So which formula weight do you use? Like, I don't know. Like, that's right. You don't know. So you can't use the mass over formula weight situation. Yes, ma'am?
Do we have any pure gases?
Oh, yeah, we do have pure gases, and that involves a third equation. And we'll talk about that towards the end of stoic. That's actually one of the easiest parts of this unit, so I leave it towards the end. But, okay. Yep.
So when does all this end?
When does this unit end? Of 2 to 3-ish weeks after spring break.
He wants to know when his suffering is
So
over.
about 4 or 5 weeks.
Yeah, it'll be basically till about the end of April, roughly. It depends on how you guys are doing, because sometimes they'll speed up or slow down, depending on how the class is doing. So I kind of flex a little bit there. But now, of course, you can rearrange this equation. You multiply both sides by the volume in liters. And you end up with this guy. Moles equals molarity times volume. Okay. So some people are like, Mr. Fletcher, I get you. Where did that go?
It's gone.
That just disappeared.
Press the reader button up in the top.
I did not want to do that.
Get ratio.
I have no idea why that left. Anyways, now somebody like Mr. Fletcher, I just don't know, like, when you divide something to get moles and when you multiply something to get moles, you need to think and you need to look at the units, okay? You're dividing mass by formula weight when you have something pure, when you're looking at stuff in grams, that kind of thing. If you have molarities and volumes and that kind of thing, you must be dealing with a solution. That means your molarity times your volume is going to get you your moles there. So that's why you really have to look at the units. If you just have the number and no units attached, you're like, do I divide, multiply, like what do I do? That's where people start really getting themselves confused. So don't needlessly get yourself confused. Just get the units on everything. All right. That brings us to the new stuff. You can call these notes concentrations of ions in solution. Concentrations of ions in solution. Notes. Now, on Monday, you guys had titration bell work. On Tuesday, you had titration bell work. And then on Wednesday, you had a quiz that looked just like the titration bell works. Guess what? Tomorrow you're going to have a concentration of ions bell work. Friday you're going to have a concentration of ions bell work. And then you're going to take a quiz that looks just like
Concentration of ions bell work.
You got it, okay? My quizzes should not really be surprising. Yes, they're always different than a problem you've already done, but they should be surprising. They're basically like, have you understood the practice that we've been doing in class and that you may have done in your packet at home, okay? My tests are very hard, but my quizzes are designed to basically be like pretty good opportunities to ace them, okay? Because they're practices that you've done pretty often. So anyways, we will have one last grade this week. It'll be a quiz on Friday. It'll be just like the bell works. It shouldn't be too bad, okay? But it's over this stuff that we're starting right now. These first couple sentences, no need to write them down. When we make solutions, they often involve ionic compounds. And to remind you, an ionic compound, that's when you got a cation, which is usually a metal on the left side of the periodic table, and an anion, which is usually a nonmetal on the right side of the periodic table. So remember, cats are positive. Remember that? Anyways.
Yeah, that horrid joke that you made.
Oh, yeah. So here's some, I got lots of bad jokes. Here's some examples of ionic compounds. So you got some NaCl, good old sodium chloride. That's basically just salt. Calcium bromide, all that stuff. Now what I have next here is highlighted, okay, indicating its importance. Now you should write it down. When ionic compounds are dissolved in water, so when you take a chunk of salt, let's say, and you dissolve it in water, they disassociate, aka break apart, into their respective ions. So when you say you're associated with someone, you are bonded to them in some way. When something disassociates, that means a bond is broken and it separates. So ionic compounds will break apart into their respective ions when you dissolve them in water. So for example, with these three right here, if I were to take a chunk of sodium chloride and dissolve it in water, which you've seen me do several times in live class, you'd maybe get a sodium flying over here, and then maybe a chlorine ion floats over here. And if I toss another one in there, maybe this next sodium goes somewhere over there, and then next chlorine goes somewhere over here. Okay? They'll separate into their various ions. Or if I drop some calcium bromide in there, maybe one of the bromines goes here, and then the calcium goes like there, and then bromine goes over here, and then maybe you do it again, and you get something like this. Notice how there's two bromines coming in with every one calcium per the formula. Lithium oxide, same idea. Okay, so maybe you got lithium there and oxygen over here, lithium right there, whatever. They'll break apart into their respective ions. Now, if we think about K2SO4, you guys recognize SO4? Anyone remember that polyatomic ion's called? Sulfate. Yep. I don't expect you to memorize that. You can always use your polyatomic ion sheet, so you don't have to have that memorized. But let's say we drop some K2SO4, some potassium sulfate, into a beaker. Which one of these beakers represents what that would look like? The one where you have the K's broken apart, the S and the O's broken apart, or the one where you have the K's broken apart from the SO4, but the S's and O's are kind of stuck together? Which one of you guys? You're going with B? What are you saying?
I thought it was B2.
You thought it was B2? Is anyone saying A?
I'm saying A. Actually, I'm with that. No, this dude, don't.
Oh. They're rolling the dice. They want to see. In this case, beaker B is actually the correct answer. And here's why. And here's why. SO4 is an ion on its own. Okay, so it's not going to break into even smaller pieces. SO4 acts as an ion on its own. So when you drop this in there, you'll get the couple of K's that pop apart because those are both ions on their own. And the SO4 will form a little cluster because it's an anion all alone. Okay, so that's what happens when you drop a polyatomic ion into a solution. All right, anyway, so let's talk about bicycles here. So let's say I dropped a bike. Let's pretend a bike is an ionic compound. If I drop a bike into water and I dissolve it, I get a couple of wheels flying out there, and then maybe like a bike seat. Okay? If I dropped another one in there, you get a couple more wheels flying around, and a bike seat. And so that's what would be floating around in that ionic solution. Okay?
No, that's just...
In light of that, if I had 100 NaCl's, how many NAs are floating around in that water? That's right, 100. How many Cl's would be floating around in that water? Okay, fair enough. If I had 100 calcium bromides dropped into a solution and dissolved them, how many calciums are floating around? How many bromines?
200.
200. Not bad. Okay. This next one, yeah, you could do that, whatever. What if I dropped 100 K2SO4s? How many K's would be floating around?
200.
How many SO4s?
400.
I heard 100 and 400. Which one is it?
400.
I heard them both again. Look at SO4s. Just SO4s? I would have 100 SO4s. And yes, there would be 400 oxygens floating around, but 4 oxygens would be kind of stuck to a sulfur. So they'd be in packages of 4. Does that kind of make sense? So there'd be 100 packages of 4 oxygens floating around. Okay? So just to clarify, that's what's going to be floating around because the ions are what are floating around, not just individual atoms necessarily. Okay, so we're talking about moles. Now I'm talking about molar, so concentration. Okay? So let's say I made a 10 molar bike solution, What is the molarity for bike seats?
1.
It'll be 10 molar. Now, do I know how many moles exactly bike seats are in there? No, but I know that there will be 10 moles of bikesteins for every liter of that solution. So maybe I don't have a whole liter, maybe I got 20 liters. I know that the ratio, the concentration will be 10 molar. What will be the concentration of my wheels? You got it. Okay. Not so bad. So it brings me here. If I made a huge thing of 2 molar calcium chloride, let's say I made, like, I filled this huge Erlenmeyer flask up with 2 molar calcium chloride. This is a lot more than 1 liter. Okay.
What do you think it would taste like?
It wouldn't taste good. Now, if I poured this into little beakers all around the room in front of you, let's say you had a little beaker of this solution all around the room, you wouldn't know how many moles you have. You don't know exactly how many calciums are in there, but you should be able to tell me the concentration of any of those beakers, okay? Because the concentration is a ratio, so no matter how many times you cut it in half, it's still the same ratio, okay? So if you took a cheese sandwich and cut it in half, you might not have 2 slices of bread and 1 slice of cheese anymore, but you know that you have twice as much bread as cheese. Does that kind of make sense, no matter how small you cut it? So if I have 2 molar calcium chloride, what is my concentration of just calcium floating around in there? It'll be 2 molar. What will be my concentration of chlorines floating around in there? It'll be 4 molar. Okay? So for every 2 calcium floating around, you'll have 4 chlorines floating around, or you could say 1 to 2 ratio. Alrighty. So here's a stopping point for you. Be careful. There is a difference between molarity and moles. That is a big difference. Molarity is a ratio of the moles of something to the water they're dissolved in. Whereas moles are just simply counting exactly how many molecules of whatever it is you're talking about you have. Okay? So molarity and moles are very different, but at the same time, the same rules apply. Okay? So if you have, like we just saw, where you just basically doubled your calciums, or I'm sorry, your chlorines to compare with your calciums, all that good stuff. And then, of course, just reminding you of these formulas once again. You don't have to write that down, but please make sure you're looking at all the units on these so you don't get them mixed up. It should always be clear to you whether you multiply or divide based on the units and what you're working with. That brings us to this worksheet right here. Go ahead and find this in your packet. Concentrations of ions in solutions worksheet. Concentrations of ions in solutions worksheet. Yes, sir. Just maybe. Just maybe. He's been waiting to say that. All right. I want to go over the first couple of problems with you. So I want to make sure you understand the format and what to expect on upcoming Bellworks and the quiz on Friday. Okay. So this first one's about, hey, if you dissolve some calcium chloride, some CaCl2 into this beaker, and has asked you questions about that. So let me make sure we're really clear on what this picture is. This is a picture of a beaker, and this circled area right here, this is like a zoomed in, like microscopic view of what's in there. Does that kind of make sense? So this is just supposed to be a microscopic view. No, we're saying that there's calcium chloride dissolved in there, which you couldn't physically see it with your eye, but you could theoretically understand what's in there at the microscopic level. So how many calciums are floating around in there?
Calciums?
Mm-hmm. There'd just be 1. And notice how I write it with the charge, and then there would be 2 chlorines floating around in there as well. And notice how I put the charges with them. Mr. Pilcher, do I have to memorize the charges? Absolutely not. You can always use your periodic table for those charges, right? So you can have calcium plus 2, Cl minus 1. Those are from your periodic table. Or if these were polyatomic ions, you can use your polyatomic ion sheet, no problem. And then it goes ahead and asks you a couple of questions. So how many moles of calcium ions are present if you have 0.01 moles of calcium chloride? So how many moles of calcium would that be?
2.
Not quite. If you have 0.01 moles of the whole thing, how many moles of just calcium will you have?
0.01.
0.01, because there's only 1 calcium in each one of those. If you have 0.01 moles of the whole thing, how many moles of chlorine will you have? You got it. We'll do a couple more of these. Let's say we're looking at number 4. It says we have 1.5 moles of aluminum sulfate So how many aluminum ions do you have? So Ian, how many aluminums are in aluminum sulfate? Okay, so if you had 2 aluminums in every one of these, how many moles of just aluminum would you have in this question?
3.
That's right. There you go. So 2 times the 1.5 that you have the whole thing. The last thing I'd like to show you, if you continue to scroll down a little bit. So in the first problems, I told you how many moles of something you have. Oh, you got 0.22 of this, 0.01 of this, whatever. And this one, I first asked you to calculate how many moles we're even talking about for potassium bromide. And then you answer the same questions about moles and molarity. Does that kind of make sense? Hey, 30 grams of solid KBr, is that pure or solution? Pure. So what equation are we going to use for that? Mass over formula weight. You got it. All right, we got 8 minutes. Get cooking. That's a wrap.